Hello. Good evening to each and every one of you. So, welcome back to our marathon series. And in this series, we'll complete the rest of the soil physics portion. So, this is soil physics part 2. Those of you who hadn't watched the soil physics part 1, I would request you to please go to yesterday's video and watch it. Okay. A very good evening to each and every one of you. So, I'm on full enthusiasm for this session because this is going to be the revision of the very important soil physics topics such as air, temperature and water. I am your mentor and my name is Purbita and I am currently pursuing my masters in IRI New Delhi in the division of Soil Science and Agricultural Chemistry. Okay, so let's begin. So first we will start with soil air. So previously when we had learned about what is the entire mineral composition of the soil, we had seen that in the volumetric composition of the soil, at least 50% of the space is dominated by water and air. So this 20 to 30% is dominated by air and the rest 20 to 30% is dominated by water. Okay, it is dominated by water and the rest is some portion of it, and the rest some portion of it is dominated by mineral matter, and that is approximately 45% of mineral matter is there and only 5% of organic matter is there. So, this is the entire composition of the soil. So, in order to understand soil physics, we also need to know about the properties of the fluids that are present, and fluids will include both the air as well as the water. So, what is soil air? So, the term air capacity, it is used to describe the aeration status of soil. Previously, when we were reading about the mass volume relationships in our soil, we saw that there were two terms. One is air filled porosity. So, who can tell me what is the formula for air filled porosity? Who can tell me what is the formula for air filled porosity? So, this air filled porosity is nothing but it is the volume of air, okay, divided by the total volume of the soil. That is the percentage of the pores that are occupied by air, okay. And another thing that you need to remember is that whenever we talk about soil air, these will be present in the spaces which are not occupied by the soil particles. So, if we see that these are the soil particles, okay, then whatever spaces are left in the soil particles, that will give rise to several pores in our soil, okay, pores. And that pores may be divided into two parts, one is macropores and the other is micropores. So, always remember whenever we talk about air, that air will be present mostly in the macropores of our soil, okay, and whenever we talk about water, it will be present in micropores of our soil. So, to judge the percentage of air that is present in soil, we actually use this term called air filled porosity. Another term is used which is called air capacity. So, that is the capacity of the soil to hold air, okay, within its pores. So, a soil that has higher macro porosity obviously will have more content of air in it, right. So, it is used to describe the aeration status of the soil. Now, why do we need to study the aeration status of our soil? Because first of all, there are different microorganisms as well as plant roots that are present, right. Living beings are present in the soil, and that living beings, they need air or oxygen to respire, okay, and to exchange the gases. So, that is why the presence of pore spaces or the soil air is very important. Now, there was a scientist whose name was Khonke, and according to Khonke in 1968, the air capacity of a soil, it will refer to the volume of the pore spaces filled with air when the soil is under a tension of 50 millibars, okay. So, it is actually the volume of the soil that is filled with air. We know that water in the soil or moisture in the soil, it is held with some kind of tension. Now, why does the soil air, it remains in some kind of tension? It is because in the soil we have several particles, and within that particles different forces will act. So, in the previous class of soil consistency, I described the different types of forces. So, it might be either due to adhesion. So, this is either due to adhesion or this is either due to cohesion. So, these two different kinds of forces will dominate, and due to the attraction of the soil solid particles with that of the air and water, the soil air will also be in some form of tension. And the air that is present at a tension of around 50 millibars, it is referred to as air capacity. And because these pores are macropores, they do not have the ability to hold water. And that is why this is also called non-capillary porosity. Non-capillary porosity, very, very important term, okay. So, are you guys with me? Are you guys with me? I want a good response in the chat box if you are with me, okay. Now, what is the difference in between the atmospheric air and the soil air? That we need to know. So, okay, so what is the difference in between atmospheric air and soil air? That we need to know. So, in case of atmospheric air, we know that the maximum percentage is that of oxygen, nitrogen, and the second most dominant thing is oxygen, and rest is carbon dioxide, okay, in the normal air, this one. Now, in case of soil atmosphere, the percentage of oxygen is slightly less. You see here it is 20.79, there it is 20.6, and the carbon dioxide, it shows a major change. At least the percentage of carbon dioxide in soil atmosphere is 10 times that of atmospheric air. This is because of the respiration of the plant roots as well as the microbial organisms that are present in the soil. Because of respiration, they will take in the oxygen and they will release the carbon dioxide. Concentration of carbon dioxide, yes, due to decomposition and microbial activity. Yes, very good, Vipin. Now, unlike the atmospheric air, the concentration of the soil air, it is highly variable. Why? Because you have a lots of activities going on in the soil, from decomposition of mineral matter, from the transportation of water, dissolution of solids, buffering and all that. There are different functions happening inside the soil because soil is a dynamic natural body. So, the composition of soil at air will also vary, and how it varies we will see in the next slides. But this you have to remember that carbon dioxide is approximately 10 times, and the oxygen percentage is a bit less, again due to respiration, because in respiration the microbes, they will take in the oxygen and give in the carbon dioxide. Clear? Now, in the next slide, we will see that how does the renewal of this soil air happens. So, that soil air, it is in a constant dynamic equilibrium with that of atmospheric air. So, the soil air, it is in equilibrium with the atmospheric air. And there are basically two steps by which this replenishment of oxygen and carbon dioxide will take place in the soil. The first one is mass flow. So, this is also true whenever you will read the nutrient transportation, okay. So, mass flow is when there will be a total pressure gradient, okay. There is total pressure gradient. That means, suppose in the atmosphere your pressure is low and in the soil your pressure is high. So, due to the overall pressure of the gases in the atmosphere, the air will move from soil to the atmosphere if the atmospheric pressure is low. So, we are not concentrating on individual percentages of gases, rather we are getting the total pressure, okay. So, in mass flow the total pressure gradient will work, and this line is very, very important, that 1 centimeter rain over an area of 1 hectare will contain approximately 4339 grams, that is 3000 liters of oxygen at 20 degrees centigrade at atmospheric pressure. So, this is a standardized line. They have measured that when rainfall happens, what is the percentage of oxygen that is contributed by rain, okay, into the soil. Next thing is diffusion. So, whenever we talk about diffusion, we have to concentrate on the partial pressure of each and every gas. So, we have to take into account the partial pressure of oxygen, carbon dioxide and nitrogen. So, even if your atmospheric air is at a lower pressure than that of soil air, if the partial pressure of oxygen in your atmosphere is higher, then the oxygen will move from atmosphere to the soil. So, here we will concentrate on individual partial pressures of each and every gas. Now, this diffusion process is more important than that of mass flow, because in case of soil, we require oxygen as carbon dioxide as the two major gases. We are not concerned with that of nitrogen or the other inert gases, but oxygen and carbon dioxide are the two most important gases that maintain life, right? So, in order to replenish those, if we take into account the total pressure gradient, that won't work, because in the total pressure gradient maybe nitrogen is also there, okay, maybe inert gases is also there, maybe carbon dioxide and oxygen are there, but their percentages is low. So that will not work, and that is why diffusion is the most important process of renewal of soil air. Clear? Now, this diffusion of gas is governed by a particular law which is called Fick's law of diffusion. And according to Fick's law of diffusion, the flux of a gas across a plane is proportional to the concentration gradient. So, whenever you will see the different laws related to heat, water, each and every time a term called flux will come. When we will read about soil water, we will also see that flux comes. So, what is flux? Flux is nothing but it is the volume of air per unit area per unit time. Okay, volume per unit area per unit time. So, this quantity is called flux. So, you can either represent it as liter per centimeter square per second or centimeter cube by centimeter into second, whatever, but it will be volume. Okay, and we express the flux as as small q. We express the flux as small q. Okay, and the volume we express it as capital Q, the area as A, and time as t. So, whenever we will talk about flux, we have to remember that in case of flux, suppose we want to measure the flux through this surface. Okay, so we will always have to take any quantity that has a flux in the perpendicular direction. So, if this is the surface, then the direction is 90 degree. Okay, so flux is always measured in the direction perpendicular to that of the flow. So, Fick's law actually states that what is the flux of a gas, and here the diffusion coefficient of oxygen. Okay, so higher the diffusion, higher the concentration of a gas, so it is directly related to the concentration gradient. You can also say it is directly related to the pressure gradient. Either it is pressure gradient or it is concentration gradient, same thing. So, whenever we talk about that, there is a constant which is called diffusion coefficient, okay, that comes into action. So, the gases that will have higher diffusion coefficient, they will have a higher tendency to move, okay, or to pass. Now, the diffusion coefficient of oxygen is about 1.25 times that of carbon dioxide, and the rate of carbon dioxide and oxygen in the air is nearly 10,000 times greater than that of water. So, this is a very general concept that the diffusion of gases, suppose I am writing here the diffusion of gases, their order will be obviously in air, then in water, and then in solids. Okay, so this is the order of diffusion. So, in case of air, the gases will be able to rapidly pass through. In case of water, their diffusion will be less. And see, here they are stating that the diffusion coefficient will be approximately 10,000 times less. What is? I cannot understand your question. Where is it written? Okay. So, where is it written? Now, the value of diffusion coefficient in the soil will usually vary from 0.6 to 0.8. This is also very important term. And the characterization of the soil aeration status. So, how can you characterize that whether or not your soil is aerated? You can either go for the air filled porosity, Q, G, I, old I cannot get you actually, Shomik, what you are actually trying to say. So, the value of diffusion coefficient, it will actually tell you the tendency of diffusion of these gases, and as I was stating that how can you characterize whether or not your soil has sufficient air? So, you can do it with the help of either air filled porosity, okay, or you can measure the chemical composition of your soil with the help of gas chromatographic or chemical chromatographic methods, or you can also go for another method that is called oxygen diffusion rate. So, this oxygen diffusion rate is the best method to characterize the aeration status of a soil, and this oxygen diffusion rate or ODR, it is measured with the help of platinum microelectrode. Platinum microelectrode. So, here you will take a cathode and an anode, and you will actually place it inside the soil pore spaces, and by the rate of reduction of oxygen, You are going to measure that how many number of oxygen molecules are getting reduced at a particular electrode, and the higher the number of reduction, the greater will be your soil aeration status. And here we actually measure oxygen because oxygen is the most important gas for the survival as well as respiration. It not only participates in respiration but also participates in photosynthesis. So that's why ODR is the best method to characterize the soil aeration status. Now, along with, okay, so let's first finish the ODR. So, the rate at which oxygen is replenished, okay. So, ODR is nothing but the rate at which the oxygen is getting diffused in or out of the soil. So, the ODR meter, it is used to measure the ODR as I had just mentioned, and it has a critical value. It is 20 into 10 to the power minus 8 gram per centimeter square per minute, it will be, below which the growth of roots of most of the plant cease. So, for your soil, you require a minimum percentage of oxygen or carbon dioxide. So, for getting a minimum percentage of oxygen or carbon dioxide, your critical value of oxygen diffusion rate should be 20 into 10 to the power minus 8 gram per centimeter square per minute. Please mind the unit. Now, who can tell me that what is the minimum percentage of oxygen that is required by the roots, and below which the root growth will stop? What is the minimum percentage of oxygen required by the roots below which the root growth is stopped? Ma'am, here it is written, okay. Okay, QGI, it is actually a term, okay, it is flux, yes, Q is the flux of the gas and GI is normal to X direction. Now, what is GI? Normal to X direction. Just wait a second, I will come to that. Yes, so it is 10%. Okay, so Soumik has a question that in old IEEE maybe it is given as QGI. See, your soil is always a three-dimensional system, right? It is three-dimensional. So, because it is three-dimensional, it will actually have three axes, okay? Your soil will have three axes. One will be, suppose this is X, this is Y and this is Z, okay? Your soil is a three-dimensional body. So, whenever we actually give these laws, Fick's law of diffusion or that, we always say that in Fick's law of diffusion, just let me rub this. So, in case of Fick's law of diffusion, we will always say that the Q, it is directly proportional to dC by dt, right? Sorry, dC by dx. This is the concentration gradient, right? This is the concentration gradient. dC is the change in concentration and dx is the per unit distance where the concentration is changing. But here we are only calculating dx, right? Only we are seeing this plane, that is the x plane, this one. But there are other two planes as well. There is y plane, there is z plane, right? So, we should not write it like this. We should write it as this is proportional to this. This is a sine, inverse triangle, and this triangle sign, inverse triangle sign is called nabla. Nabla, or it is also called as vector differential, sorry, nabla or vector differential. And whenever you write this sign called nabla and then you write dC by dx, that means that you are actually taking all these three axes together. So, now the equation will become, just let me omit this. Now, your equation will become Q, it is directly proportional to nabla into dC by dx plus dC by dy plus dC by dz. And now, you can omit this nabla term. Clear? So, whenever you have, because of simplification in JRF level, we are only considering one dimensional flow, but because soil is a three-dimensional body, we have to take into account all the three axes, that is x, y and z, and for that we use that thing, that is normal. So, if we are taking the x axis, we will take GI because it is perpendicular to the x axis, sorry, not x axis, it is perpendicular to this plane, okay. If we want to take this plane also, sorry, if we want to take this plane also, we can do that. And similarly, if we want to take this plane also, we can do that. So for different axes, it will vary, and that is why it is written as GI. Clear, Swamik, your question? So this is just a bit of higher level thought. The same thing you will find in Darcy's law, the same thing you will find in Fourier's law of heat transfer. So in all the cases, just for our sake of simplification, we will take only one axis, that is dC by dx. Clear? Okay. Now moving to another term. Okay, is it clear to each and every one of you? Now moving to another term, which is air permeability. So whenever we talk about all these fluids, that is water and gas, permeability in the soil is very important. If the air and gas cannot pass through the soil, there is no question of all these mechanisms of renewal. So air permeability is the ease with which air can transmit inside the soil, and it will indicate the readiness of the soil to transmit gas when a difference in pressure builds up. So always remember that all the flows, okay, whether it is flow of water, whether it is flow of air or heat, whatever, in physics, all the things will move they will move along the gradient. Along the gradient means they will move from a zone of higher concentration to a zone of lower concentration. That is along the gradient. Okay. So they will move from a zone of higher concentration to a zone of lower concentration. So whenever there is a difference, if there is no gradient, if the pressure in the atmosphere and that of soil is same, then there will be no flow of air, water or heat. Okay. So that is why there needs to be a particular difference in pressure. And special instruments like air permeameter or gasometer is used to determine the air permeability. So this is also very important. How can you determine the readiness of your soil to transmit gas? But among all these methods, I said that ODR is the best one with which you can determine the soil aeration status. Clear? Now, what are the factors affecting ODR? Suppose you have the soil and the soil is in an entirely saturated condition. So whenever your soil is saturated, that means how much percentage of your pores are filled. Percentage of filled pores, please comment in the chat box. If your soil is saturated, how much percentage of pores are filled in your soil? That I want an answer to. So your soil is saturated, that means you are providing irrigation and actually 100% of your pores are filled. So if all the pores are filled with water, then there is no space for air. Yes, it is 100. So if all the pores are filled with water, then there is no space for air to enter, and that is why the ODR will decrease. So here it is written soil water tension. So what does tension means? What does soil water tension means? Whenever you are in tension, that means you are in pressure. Clear? This is very in literal terms. Whenever you are in tension, that means you are in pressure. So there is a lack of something. So whenever it is tension for soil water, that means there is a lack of water in your soil. Low quantity of water is present, and if the soil water tension is more, that means the ODR will also be high, because here they are talking about water tension. But if the same thing would have been only soil water, if I wrote only soil water in here, then if the quantity of water increases, then the tension will decrease. So it will be inversely proportional to the oxygen diffusion rate. So these two things you should remember. One is for the soil water tension and the other is for the soil water. Then soil texture. So tell me, which of the soils they are more permeable? Sand, clay or silt? Sand, silt, clay. What will be the oxygen diffusion rate in case of sand, silt, clay? That you can tell. And the depth. So when we go down, what happens? Compaction increases. So compaction will increase if we go down. So compaction will be greater in where? Subsoils than in surface soil. So obviously with the soil depth, the ODR will decrease. So it is inversely proportional to the oxygen diffusion rate. Yeah. So in case of sand, there will be higher ODR because sand has greater number of macropores than that of clay or silt. And in case of soil compaction also, the ODR will decrease because we are decreasing or we are compressing the pores, right? So, these are all the factors that affect the ODR, very, very important, okay. Now, so that was all about soil air, but one thing I just wanted to mention is, suppose you have a sand, suppose you have sand and you have clay, and both are in two conditions, one is wet condition and the other is in dry condition. So, whenever your sand is in wet condition, the percentage of saturation is same for both of that, it is also saturated, it is also saturated. So, in this case, the diffusion of air, okay, in case of wet condition, the diffusion of air, it will be less for clay, because we will see when we read about hydraulic conductivity that for sand, the saturated hydraulic conductivity is more than that of clay. So, in saturated condition, the sand is able to transmit more water than that of clay, and that is why the diffusion rate in sand will be less in case of saturation. So, here the diffusion rate is less for this one, okay, for this one in case of wet condition. But similarly, in case of dry condition, clay has more ability to hold water. So, the diffusion rate will vary in case of clay. So, always remember, whenever we talk about this sand and clay, we have to, whenever we talk about air, we have to also take the complementary component, that is water. So, there is a relationship between water and air. If water is more, then air will be less, that is it, okay. This is very, very simple. Now, coming to our next topic, as that of soil temperature. Any questions with soil air so far? So, now coming to our next topic, which is soil temperature. So, you all know, I think you all have read basic physics, that is the difference in between heat and temperature. Heat is the hotness or coldness, that is the amount of energy that is stored in the body. So, heat is the energy and temperature is the measurement of that energy, that how you can measure the energy. So, soil temperature, we have seen that in case of taxonomy, this temperature regimes and moisture regimes, they are very important in which level of taxonomy? Please comment which level of soil taxonomy they are used. Which level of soil taxonomy the soil temperature and soil air are used, please comment. So, the soil temperature will also govern the different vegetation in the soil, the percentage of air, percentage of water, as well as what will be the soil properties. Yes, very good, Vipin. So, these all are very important at family level classification. Now, coming to the thermal properties of soil. Always remember, if your outer temperature or atmospheric temperature, nowadays it is very hot in here. So, if it is around 42 to 45 degrees centigrade, your soil will not have that higher temperature. So, that soil temperature will always be less than that of atmospheric temperature, and that is governed by different thermal properties of the soil. So, what are these thermal properties? You know that a soil, depending on its textural classification, depending on the mineral composition of the soil, yes, very good, Vangala. Depending on the mineral composition of the soil, the heat capacity or the thermal properties will vary. So, first let us take a look what are the different thermal properties. Number one is your heat capacity or thermal capacity. So, it is nothing but what is the amount of heat that is required to raise the temperature of a body by 1 degree centigrade. And here we will not take into account the volume, the area, the quantity of the body. For normal heat capacity, we will only take what is the amount of heat required to raise the temperature by 1 degree centigrade. So, its unit will be calorie per degree centigrade. But when we talk about, okay, now this is not thermal conductivity, when we talk about specific heat, in that case we will consider what is the unit mass of the substance. So, either you can take it in mass unit, or we can also say that we have volumetric heat capacity. So, for volumetric heat capacity, we have to take calorie per centimeter cube per degree centigrade. Okay, so we have to always take into account the volume. Now, I think that you are very much aware with the basic units. So, can anybody tell me what is the relationship between calories and joule? 1 calorie is equal to how many joules? 1 calorie is equal to how many joules? Very easy question. Now, the third property is thermal conductivity. I want the answer in the chat box. Now, the third property is thermal conductivity. So, these are the properties by which the soil or any body can hold the heat, right? Can store the heat energy inside them. But conductivity is something by which they can transmit the heat. Conductivity 100. Oh my god. So, and anybody else? Any guess? 4.9. 1 calorie is equal to 4.2 joule, guys. 1 calorie is equal to 4.2 joules. Please do remember. And another thing, very interesting thing is that calorie is a CGS system. Calorie unit, it is in CGS system. What is happening, I don't know with this board today. So, calorie, it is in CGS system and joule is in SI system. Mostly wherever we see that the calorie, that CGS system units are less than that of SI system units, but heat is one of the exceptions where the joule or the SI unit is less than that of the CGS unit. Okay, and another unit is not sure, ma'am, and another unit is resistance. Okay, so that is another unit. Okay, now, so always remember that 1 calorie is equal to 4.2 joules. So, thermal conductivity is something by which you can transmit the heat. So, the quantity of heat that is transmitted through a unit substance per unit cross sectional area, okay, through unit temperature gradient is called thermal conductivity. So, I just write it down, and this is called Fourier's law actually. Fourier's law of heat flow, and same here, that he said the flux is directly proportional to the temperature difference, okay, into the distance. No, okay, just if I write Q by AT, it is equal to T2 minus T1 by X. Okay, so it is this is the unit of this is thermal conductivity over here, coefficient of thermal conductivity. So, we will come to Fourier's law later on, but just to make you understand the unit, it is expressed in calorie per second per centimeter per degree centigrade. So, just let me check once if I had included Fourier's law. Okay. So, the quantity of heat that is transmitted through a unit of a substance per unit cross sectional area per unit temperature gradient per unit time. Okay. So, the temperature gradient will be this T2 minus T1 divided by X, and to make it equals to, we will have to write K as the coefficient of thermal conductivity. Okay. So, Q by AT is equal to K into T2 minus T1 by X, or we can here also write, instead of this equation, we can write is equal to K into dt by dx. So, this is also, you can say that this is the temperature gradient, and here K is the coefficient of thermal conductivity for a particular body. So, here let us see that how the unit comes. So, for Q, we can write that it is calorie divided by, for the area we can write it is it as centimeter square into T as seconds, okay, is equal to K into this dt is degree centigrade divided by centimeter. So, if I cut it out, then it will be calorie per centimeter per second per degree centigrade. So, this will be the unit of thermal conductivity. So, this is how the unit of thermal conductivity came in the previous slide. Okay. Now, thermal conductivity, as I mentioned, that it will also depend on the moisture content, the texture, the structure and the mineralogical composition. Why? Because water, okay, or all the other minerals, they have their own thermal conductivity values. And this is very important that it will vary in this order: sand first, then loam, then clay, then peat or organic soil. And thermal conductivity will increase with the increase in wetness of the soil up to a certain limit. So, I will just show you. These are the specific heats of different soil constituents: quartz, soil minerals, organic matter, water. Okay. So, along with that, you will also have soil air. You will also have soil air. Okay. That you have to remember, but these organic matter, water, minerals and quartz very important. Ice also is there among the soil constituents. So, depending on the specific heat means what? That it has a greater tendency to hold the heat. So, the higher the specific heat of a substance, the lesser will be its thermal conductivity, because it won't want to transmit that heat. Okay. Now, another thing is that compact soils have higher thermal conductivity than loose soils. So, just imagine that this thermal conductivity will actually depend on how close the particles are together, closeness or proximity. If the particles are attached to one another, suppose here there are several spaces, suppose this is our entire volume of soil and this part it is empty. So, empty means it has air. Now, again we know that air is an insulator, insulator to the flow of heat. So, if a soil has plenty of pore spaces and they are filled with air, then the thermal conductivity will not be that much. But at the same time, if I replace all this air, suppose I am replacing all this air with water. If I am replacing all this air with water, then water will do what? Water will maintain a continuity or a flow. Continuity or a flow is maintained and it will increase the thermal conductivity. So, here it is written that in case of wet soils or with increase in wetness, the thermal conductivity of a soil will increase, but it will only increase up to a specific value, beyond which there will be excessive dispersion of particles due to wetness. The soil will become very soggy, puddly, and that is when the thermal conductivity will decrease. Clear? Clear the thermal conductivity part? Now, the fourth most important property is thermal diffusivity. So, it is nothing but it is the ratio of thermal conductivity to the volumetric heat capacity. So, I had taken thermal conductivity to be calorie per centimeter second degree centigrade and volumetric heat capacity as calorie centimeter square centimeter cube into suppose degree centigrade, right. So, I will be omitting this. Okay, the second one will remain. I will be omitting this and your final answer is centimeter square per second. So, this is how the unit of thermal diffusivity came. And in case of thermal diffusivity, very important property, it actually tells you that what will be the rate of heat transfer from one body to the other. Next is thermal retentivity. So, it is just the opposite of thermal diffusivity. So, 1 by thermal diffusivity you can say, and here the unit will be second per centimeter square for thermal retentivity. Now, another term, it is also basic class 7-8 knowledge, that what is latent heat. So, latent heat, it is the minimum amount of heat that is required in order to change the state of a body without changing its temperature. So, in case of latent heat, there will be no change in temperature, but there will only be a change in state. So, please comment the the latent heats for two things. One is fusion and the other is vaporization. So, can you please comment the values of latent heat for all this? Okay. Now, coming to another concept, which is the concept of albedo. Heat. What is heat? Okay, I just wanted to know the latent heats of fusion and latent heats of vaporization. So, 80 for what? So, latent heat of fusion, it is 80 calories per gram, and for the latent heat of vaporization, it is approximately 537 to 540 calories per gram. Okay. Yeah. 540 calories per gram. And please do remember the SI units as well, what are the values in SI system. Another thing is that in case of soil water, because the soil water is in a constant tension, the soil moisture is in a constant tension, so the forces holding the soil water will be more than that of free water. So, in case of soil water, the latent heat of vaporization is equal to 580 calories per gram. So, you see that it is approximately 40 calories more than the normal latent heat of vaporization. For 20 degree is 590 and for 100 degree it is 537. Yes, so it will also depend on the temperature. But I am talking about 100 degree only because water vaporizes at 100 degrees. But for the soil, you have to remember that it is approximately 580 calories per gram because the soil water is always in a tension. Okay. Now coming to another concept, which is albedo. So that albedo will also reflect the temperature of your soil, and it is the amount of energy that is reflected divided by the amount of energy that is absorbed. But always remember that both these radiations are short wave radiations. Short wave radiations. So, how can you distinguish in between short wave and long wave radiations? Always remember that whatever radiations are emitted from the sun or from the bodies that have a very high temperature, that will fall under the short wave radiation, and it has a wavelength range of 1.5 to around 4. Wavelength range to 1.5 around 4, suppose I am talking about micrometers, yes. And for the long wave radiation will be emitted by earth's surface that have a lower temperature. So, it will be from 3 to beyond, okay, 3 to beyond. So, this is the entire range in case of your electromagnetic spectrum, that what is short wave and what is long wave radiation, and always remember that albedo is for short wave radiation only. So, if the albedo is higher, that means your reflected energy is higher than that of absorbed. So, you are reflecting more than that getting absorbed. So, in that case the temperature will always decrease, and if it is equal, then there will be no decrease in temperature, there will be no change in temperature, and if the albedo is less, that means more and more heat is getting absorbed, and the albedo value, it will range from 0 to 1. So, always remember, it is a discrete variable, sorry, it is not a discrete variable, it is a continuous variable, but it can lie anywhere in between 0 to 1. So, for 0, what will happen? There is no reflection, entire thing is getting absorbed. So, 0 is for a complete black body. Okay, that entire amount of heat is getting absorbed. A black body will absorb 100% of the incidental radiation, and normally the mean albedo of our earth is 0.36. So, this is what you have to remember with respect to albedo. Now, these are the things that are related to albedo. If your color is dark, that means it will absorb more moisture. If there is water present also, that means it will absorb more moisture. So, if your soils are wet and compacted, wet compacted soils, they are poorest insulators to heat. Poorest insulators to heat. They are the best conductors or the poorest insulators to heat. Okay. So, dark colored soil will absorb more albedo, more the wetness, it will also absorb more albedo, and it will also depend on the latitude and the altitude. That means whether it is present in the equator, whether it is present in the poles, etc., etc. Albedo of absolute white surface is 1, and for you guys, you have to remember the values of albedo for ice, water, forest, grassland, blah blah blah. So, all of that is given in this book called treatise. Just go through it. Remember the values for albedo. Okay. Now, what are the factors affecting the soil temperature? The composition of the soil. So, as I rightly mentioned that, I mentioned all the specific heats of different minerals. So, accordingly, varying the composition will vary the temperature. Then the structure. If your soil has a very good structure, very well aggregated structure, then it will pass the heat rapidly. Soil texture also sand, then silt, then clay, like that. And soil moisture also I mentioned that if your moisture percentage is more, then your soil temperature will be more. Another thing which is important is tillage. So, whenever you do tillage, you will do what? You are manipulating the upper surface of the soil or the top layer. So, tillage actually it will increase the soil temperature. It will increase the soil temperature because it will concentrate heat in the topmost layer. And another thing is that the soil temperature at a depth of 50 meters, at a depth of 50-meter depth is considered to be ideal, that is free from fluctuations. Our soil, it is the temperature is rapidly fluctuating in the surface soil because it is in direct contact with the atmosphere. So, there are frequent processes of heat loss and gain, and at a 50-meter depth you will find that all that processes they are somewhat static, and now there are not major fluctuations happening in the soil. So, this is considered as the ideal temperature of the soil. So, whenever we bring about the soil temperature regimes or the moisture regimes, for the temperature ones actually we measure the soil temperature at 50 meters depth. Okay. Now, what is the importance of soil temperature? So, each and every microorganism they will also need. In case of drainage, it will increase temperature. Please explain, ma'am. Okay. So, what happens? What happens? Okay, I am explaining it over here. So, in case of drainage, drainage means what? In case of drainage, there is loss of water, right? Now, I mentioned initially that if your water was there, suppose if your water is there in the soil, it will have more thermal conductivity. It will have more thermal conductivity because it will help in maintaining a continuity of the pores, continuity of soil. It will maintain the continuity of the soil because water is there, right? So, it will maintain the continuity of the soil and it will have more thermal conductivity. More thermal conductivity means if this is your surface soil and this is your subsurface soil, the heat, it will rapidly flow from surface to the subsurface because the thermal conductivity is high. So, this happens when water is present. But when you drain it out, when you are draining out the water, you are doing what? You are creating some air spaces in it, right? And air, it is an insulator to heat. So, it will not tend to pass that heat from the surface. So, most of the heat will be concentrated in the surface. Now, it cannot pass. So, that is why it raises the soil temperature. Got it, Vipin? Got it? Okay. Now, what is the importance of soil temperature? So, these are all the practical temperature percentages that you have to remember for microbes, for the plant roots it is there, and for the microbes it is there. So, they require approximately 20 to 35. Okay, so one was 25 to 30 degrees centigrade, I have suppose, yeah. So, it is 25 to 35 and the rest is 20 to 25 degrees centigrade. Please check this value once in old ISSS. I cannot remember it exactly. So, this is given in old ISSS, the optimum range of temperatures for root and microbes. It is somewhere around that, but please do check the correct values. Okay. Now, what is biological 0 and below 5 degrees centigrade? Ma'am, please revise and soil color graph of ISSS. What is the soil color graph of ISSS? I don't understand, Swami. Okay, color graph of ISSS. So, hue, value, chroma, that soil color you are talking. We will come to soil color later on. Okay, first let us concentrate on temperature. So, this organic matter, okay, what I was saying, okay. First, below 5 degrees centigrade, everything will stop, enzymatic activity will practically cease. So, this is called biological 0. And these are the different methods by which you can measure the soil temperature. Either you can do it in contact with a particular instrument, or you can also do it for non-contact methods. So, please take a look what are the different contact and the non-contact methods. In case of non-contact, there will be no contact in between the soil and the instrument. Easy. So now we will come to soil water first. Okay. Okay, so at Soumik's request, we will start with soil color first. Okay. So what is soil color? Soil color is nothing but it is the visible radiation. So color, we will only see color when it is in between 400 to 700 nanometer, right, when it falls under the visible range. And in case of soil color, whatever the mineral constituents are present, accordingly they will impart different colors to the soil, and that is determined with the help of Munsell color chart, and it has 199 different colored chips for the soil, and each color chip has three components, that is hue, value and chroma. This hue, actually it will indicate that what is your dominant soil color. The hue will indicate what is your dominant soil color, either it is red, yellow or green. The value will indicate the relative lightness or brightness or darkness of the color, that is it is always in between 0 to 10, and the chroma is in between 0 to 8, and that will give you the purity or strength of color. Okay. So, these three processes or these three, sorry, not processes, terms you have to remember. And if suppose your organic matter content in your soil is high, then the soil will be darker in color, and that is why it will have a less value. Value will be less, chroma will be less. If your soil is rich in organic matter, then your value will be less and chroma will be less. But we had read about ochric horizon, okay. You have 6 composition of color. Okay, I will explain the graph, don't worry. So, if your what I was explaining. So, yeah, chroma, if it is less and value is less, that means organic matter percentage is more in your soil. But we had read about another horizon which is called ochric horizon, okay, or albic horizon. So, this ochric horizon is epipedon, albic is endopedon. So, in both the cases, they have very high value. High value means light color, low value means dark color. So, in this way you can remember. Okay, now let me just see the graph once. I haven't brought the graph here, but let me just check it once and then I will explain. Okay. Just a second. Okay, just give me some time. I'll just find the graph out and then I'll explain. But before that, let's start with soil water. Okay, I'll explain the graph. Don't worry. But I have to just find it out. Soil color chart. Okay. Okay. So now, okay, okay, I just found it out. So, so what it states is that in case of Munsell's color chart, we will have one straight line. Okay, we are having one straight line, and within that straight line, we will actually have values from. Okay, so this is not a straight line. Just let me draw it once again. So we will have one straight line. Sorry, we'll have one straight line, and within that we have values from 0 to 10. Okay, we'll have values from 0 to 10, and this one, it is value. This perpendicular component will represent the value, that is the relative lightness or darkness of our color. Now, there is another component which is round in shape. Okay, and that component is the hue, 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 that will give you the dominant spectral color. And there is the distance in between the value and the hue. So, that distance will be indicated by your chroma. Okay, so this is the entire chart. Now, for the hue, that hue can vary in between red to yellow. Okay, red to yellow, that can vary, and it can be of different compositions. Suppose red, then yellow red, then green yellow, green, blue, blue, okay, then purple, reddish purple, like that. So, you can have different compositions, and for each and every one you can assign a value. For example, if I take suppose 5 YR, I can assign it to be a value of 5 YR. I can even assign it a value of 7.5 YR or 2.5 YR. So, first you will have to identify the dominant spectral color, whether or not it is R, YR, GYB, like that, and then you can assign a value depending on what color chip it is, okay, in case of hue. And in case of chroma, I mentioned that it is from 0 to, okay, yeah, so chroma is from 0 to 8. These are the 8 different categories for chroma, and then we have the value over here, it is 0 to 10. So, whenever we write the soil color, then we write it in this way. First we write it as hue, then we write it as value, and then chroma. Okay, so first suppose 2.5 YR, 5 by 6. So, in that case this 2.5 YR will denote the hue. So, first we will judge it from this circle, and then for the 5 YR we will denote it with the help of value where this falls, okay, where this circle is falling in the perpendicular line, and what is the distance from the mid position to the end, it is called as chroma, and it will be given in the last. So, clear? This is a very simple chart, for explaining the hue, value and chroma. And mostly remember, generally for your highly weathered tropical soil, it will lie in the value of R, YR, like that. But if your soil is moistened, or if it is waterlogged, then it can belong to this blue green, okay, grayish green, like that. So, in that case also it will have a very low chroma. Okay, soil color clear. Now, coming to soil water. So, this is our last topic for soil physics, and soil water, as I mentioned, that this soil water, it will always be in some kind of, okay, it will always be in some kind of tension because it is always held. So, the soil water will always be at some kind of tension than that of free water. So, free water is whatever is present in your surface, okay. So, whatever is present in your surface, that is free water. Now, there are different zones of water in the soil profile. This is very important. First is soil water zone or root zone. So, you know that roots, they all grow in the topsoil layer or surface soil, and it will extend from the soil surface to the bottom of the root zone. So, this is the uppermost zone. Then we have vadose zone. So, from here you can see, I suppose this is the root zone, the topmost thing, and in the lowermost region you have the groundwater. So, the vadose zone will be present somewhere in between the root zone and that of the groundwater. Okay. So, the vadose zone, it is characterized by an unsaturated condition. Just imagine with the help of a story that you have given irrigation to a field. So, firstly the water will concentrate in the surface layer, right. So, your surface layer will be most saturated, but as time passes the water will slowly be absorbed by the lower layers. So, your lower layers are still unsaturated, but your top layer is saturated. So, because we provide irrigation to the root zone is always saturated. So, it is called soil water zone. But whenever we go down, then the percentage or degree of unsaturation begins or increases, and that is called vadose zone. And finally, when we reach the groundwater table, suppose the groundwater table is present, then the soil that is just in contact with the groundwater, it will always be saturated because the water is constantly getting seeped. So, that is called as the capillary fringe zone. So, it is nearly saturated due to capillary rise from the groundwater. And all these structures that store the groundwater, they are called as aquifers. Okay, aquifers are the structures that store the groundwater, and the parched water table is an aquifer that will occur above the regional water table. So, here from the figure you can see that this is the aquifer, underground water storage structures. And what is a parched water table? Parched means it is present some distance above that of the normal aquifer. And here also I wanted to tell you some terms, that is aquiclude is there, aquifuge is there, and aquitard is there. So, whenever you have aquiclude, that means they can include the water. So, they will themselves be impermeable. They are impermeable, but they will hold the water. For example, porous rocks that are pumice. Okay, these are porous rocks. Aquifuge on the other hand, they will be impermeable to water and they will also not store water. So, storage also not done. But in case of aquitard, they will be somewhat permeable through seepage. Okay, they can seep the water. So, these are the three additional terms instead of this aquifers that you can remember for your general knowledge. Now, coming to the properties of water, very easy thing. This water H2O, it has a this tetrahedron kind of structure, and you know that one of the basic properties of water is hydrogen bond, and water is also called as a universal solvent. It is polar in nature, it is a polar molecule, so it will always, polar means it has a particular dipole moment. Polar molecule means it has a particular dipole moment and it will only dissolve the salts that are polar. That means they can be dissociated with that. And this is the radius, bond length, angle, very easy. You can also write it as 104.5 degree. And here the water structure, it has two lone pairs, that also you know, that if this is O and this is H, then it will be two lone pairs. And why is it 104.5 degree? Because the lone pair repulsion will be high. The lone pair repulsion is very high, and that is why it shifts this angle of 120 to 104.5 degree. This is also very clear basic chemistry. Now, hydrogen bonding is it, each water molecule will form 4 hydrogen bonds in liquid water. And density is, we have seen the properties of anomalous expansion of water, where up to 4 degrees centigrade the density will increase and the volume will decrease, and density, it is inversely proportional to volume. Cohesion and adhesion I had discussed previously. Now, coming to viscosity. So, viscosity is just opposite to permeability or transmittivity. Viscosity means you are resisting the flow of a fluid. So, it is the resistance of flow to a fluid, okay, and its unit is Pascal into second. So, we can always express the viscosity with the help of this formula, that F is equal to minus eta A into dV by dx. So, F it is force, if we can say that this is force, this is area, and this is the velocity gradient, that is dV by dx, and from there we can calculate the units of viscosity. So, eta will be is equal to F into dx by A into dV. So, put here the units of force, the units of length, velocity and area, you will get that viscosity, and it is always m L to the power minus 1 T to the power minus 1. So, this will be its dimension. So, the dimension and its unit is also very important. So, it is kg, meter to the power minus 1, second to the power minus 1, or its unit is poise. Okay. So, who can comment that what is the viscosity of water at 25 degrees centigrade? What is the viscosity of water at 25 degrees centigrade, and what are the other units of viscosity instead of poise? Okay, that also comment. So, the ratio of viscosity to the density of a fluid is called kinematic viscosity. So, whenever we talk about the ratio of viscosity to density, it is called kinematic viscosity. So, this kinematic viscosity is actually something else, a bit higher level concept, and that will tell you the ability of the fluid to flow. So, it is 0.089, okay. It is not 0.00, it is 0.089 and I want the unit. It is 0.089 poise, or we can also write it is 1 centipoise. 1 centipoise we can also write, and the other unit of viscosity is poisuli. Okay, just so let me write here only. So the other unit of viscosity will be poisuli, and 1 poisuli is equal to 10 poise. So these are some of the things or relationships that you need to know. Typing mistake, ma'am. Okay, yeah, okay, fine. So these are some relationships regarding viscosity that you need to know. And also remember that we measure the viscosity at 25 degrees centigrade, but whenever we talk about surface tension, we measure it at 20 degrees centigrade, that is 72 dynes per centimeter. And surface tension is nothing but it is force per unit length. Force per unit length, so that is dynes per centimeter. Very easy. Now, there are some properties of water that you need to know, because we are studying the soil moisture, right? So, it is not free water. It is the water that is present inside the soil and at a particular tension. So, there comes soil, there comes contact angle. So, what is contact angle? Whenever water is resting on a surface or a liquid is resting on a surface, it will form a particular angle with the surface that we can judge by Young's equation. And from the figure you can see that if it is hydrophilic, then it will be acute. If it is hydrophobic, then it will be obtuse. So for the acute one, we say that it is, for the acute one, we say that it is wetting surface, and for the obtuse one, it is non-wetting. Okay, so there are some wetting fluids as well as non-wetting fluids. Whenever your surface will be wet, then your contact angle will increase, and that we say with the help of Young's law. So this is hydrophilic and that is hydrophobic soil. So when it is philic, that means adhesive force is more than cohesive force. Adhesive force means the soil water interaction, because it wets the surface, that means it wants to get in contact with the soil. So the adhesion will be more than that of cohesion, and for the hydrophobic one, it will be reverse. Clear? Second most important property is capillarity. So I just tried to explain a bit capillarity in the previous lecture. So here it is given in details. So the surface of water, you can see that whenever water rises up, because water is a wetting fluid, the meniscus will always be concave shaped. Okay. But if suppose I had taken a non-wetting fluid here, for example mercury, then the meniscus would have been convex shaped. So for hydrophilic surfaces, the meniscus is concave, and for the hydrophobic surfaces, it is convex. Another thing here, okay, just wait a second. So the surface of water is curved, and that curved surface is called meniscus. So in the hydrophilic tube, it is concave and that is convex. And this is very, very important. So this is called Jurin's law. This is called Jurin's law, and that will tell you that what is the relationship in between height and that of radius of a tube. Okay, height and radius of a tube as well as its contact angle. So after putting all the values of the surface tension, that is 72.7, the density of water, the acceleration due to gravity, we get this H is equal to 0.3 by D, or you can also write as it is 0.15 by R. Both way the question might come. Okay, 0.3 by D or 0.15 by R. And this question is every year it is repeated. What is the relationship in between height and the radius of a particular tube? So always remember that lesser the radius, more will be the height of a tube. Lesser the radius, more will be the height of a tube. Okay, another thing I wanted to mention is, whenever you have a hydrophilic liquid, suppose this is a hydrophilic liquid, that means it is making a concave meniscus. So in case of a hydrophilic liquid, the radius of curvature, this is the radius of curvature, it will lies outside the fluid. Okay. But whenever it is a non-wetting liquid, for example this one, then the radius of curvature will always lie inside. So it will be inside. So this is just a basic thing. Okay. Hydrophilic water loving, yeah, hydrophilic means water loving and hydrophobic means water hating, and that is why it does not wet the surface. Okay. Okay, now coming to another important topic, which is the different soil moisture constants. Soil moisture constants. So, okay, sorry. So, I will not be going into that much details with the soil moisture constants, but this is just for your reference. I will just explain each and every point in brief so that you can get an idea. Okay, before that, just let me, okay. Before that, let us read the classification of soil water and then you will understand the soil moisture constants. So, we have two systems of classification, one is physical and the other is biological. Physical means you are just classifying the water based on how it is present, and biological means you will classify it based on the needs of the plant. So, first is gravitational water. You are pouring the water, and in case of gravitational water, it will easily drain due to the impact of gravity. So, it is also called free water. The second one is capillary water. So, after the gravitational water has drained, whatever water is held in between the micropores. So, in case of gravitational water, your macropores will be filled. Both macropores as well as micropores will be filled. But in case of field capacity water or capillary water, sorry, only micropores will be filled and no macropores. So, field capacity, it is in between -1/3 bars to -15 bars, that is field capacity to permanent wilting point. Okay. So, then we have the hygroscopic water. So, this capillary water is the one that plants can utilize. Hygroscopic is still you are increasing the tension, and when you increase the tension, the pressure also increases. Okay. So, tension and pressure, they are similar, but they are negatively related. So, tension is equal to negative of pressure, you can say. No, sorry, the tension is negative of potential. Sorry. Tension is negative of potential. Tension is negative of potential. So, potential actually refers to what is the amount of water that is present, or free energy of water will come to potential. But whenever you are saying that your water has a higher tension, that means there is deficiency, as I just mentioned. So, your water potential will be less, okay, if your tension is high. Now, hygroscopic water is due to the force of adhesion, and it will lie like a very thin film round the soil surface, okay, and it will be at a suction of higher than 31 bars, and this water is only available to that of the microbes, and it is in vapor phase. The second is biological classification. So, here you will have superfluous water or drainage water that is very similar to gravitational water, only held in the macropores, and this value for field capacity, it will depend on the texture. So, generally for sandy soil it is less, and for the clay soil it is more, because clay soil, it tends to absorb more water, okay, it has more water holding capacity than that of sand, and that is why it is low. Now, plants cannot utilize this water, so it will be left. Then this is the available water. Now, always remember that only a part of capillary water is available, not the entire portion. And then we have unavailable water, that is just beyond. So, please take a look at this chart. This is very important. So, for the physical classification, I just mentioned that we have gravitational water. Okay. So, see that is saturation. That means 100% water is present. In case of field capacity, it is decreasing. The water is decreasing this way. Okay. Water is increasing that way, decreasing this way. So, there is saturation, and here we have field capacity. In case of field capacity, from field capacity, the capillary water will start. And see, the capillary water is up to hygroscopic coefficient. Okay. But if you see the available water, the plants can only take the available water between FC and PWP, permanent wilting point. Okay, between the field capacity and the permanent wilting point. So, only a part of capillary water will be available, not the entire portion. Then for the rest, we will have unavailable water, and beginning from the hygroscopic coefficient, we will also have hygroscopic water. So, all this is unavailable, only this part it is available to the plants. Okay, and here the tension is also given. So, you see that as we move this side, the quantity of water decreases, but the tension, it increases. Okay. So, now let us move to soil moisture constants. Yes. So, you see at saturation it is 0, field capacity 1/3 bars, it is for fine textured soil, fine textured soil, and 0.1 bars for coarse textured soil. Then permanent wilting point is where the plants will permanently wilt. Hygroscopic coefficient is they cannot regain even if the relative humidity of your atmosphere is 99%, they cannot regain their turgidity. Then gravitational, capillary and available I had already explained. So these are the different conditions and these are the different potentials for water. And also you have to remember a few things, that is 1 bars is equal to 1023 centimeters. Okay, 1 bar is equal to 0.998 atm. 1 bar is equal to 10 to the power 5 Pascal. Okay. So these are some of the things, or 10 to the power 5 Newton per meter square. Okay, and 1 by 10 bars is equal to 2 pf. So pf is what I explained in yesterday's class. So 1 by 10 bar is equal to 2 pf. So all of these relationships you should be properly acclimatized with. Okay. Now we will come into the availability of water. No, just not the availability. Yeah, availability of water. So this availability of water, it is in between the field capacity and permanent wilting point. Now maximum water is available in silt loam, and these are a few things written, that aggregated soil, it will always have more water availability. Expanding type of clay, more water availability, and organic matter, it increases available water. Very easy. But this thing we should be concerned with, that two scientists were there. One is Weimar and the other is Hendrickson. And they were the first to give the concept of plant available water. They said that no, the entire water is not available to the plants. Okay. So you see that this is the curve for available water. The available water is increasing, sorry, the available water will first increase as we move beyond the field capacity, and up to a certain point it will be constant and then it will start decreasing. Okay. So very easy, but you have to remember that it should be in between FC and PWP, permanent wilting point. Okay. Now promotion time. So if you want to read about the soil water with detailed explanations, equations and all that, you can always subscribe to our master course. You can, if you want to practice the PYQs, because this soil physics portion is very important, then you can also subscribe to our mock test bundles, and that is available at a great discount. Okay, and JRF is only a few days away, I would say. So I would suggest that you should practice more and more questions, at least give 1 or 2 mocks per day, so that you can know that what is your level of preparation, and whether or not you can complete that entire syllabus or entire question set within time. So you can always subscribe. Okay, you are welcome if you like our teaching. Now coming to a very important concept, which is soil water suction or soil water tension. So as I was telling from so long, that tension means there is deficiency of something. Okay, so it will indicate how strongly the soil is holding the water. So if the moisture content is low, that means the potential is high, potential is also low, then the tension will be, suction or tension is high. So moisture content, it is inversely proportional to suction. These two lines state that only. And potential and suction are opposite, I just mentioned. And this chart, okay, it is very, very important, that we wanted to describe that how potential, suction, moisture content is related to plant water availability. So please take a look at this chart. Okay, it is just similar to what I explained, that how potential is related to the plant water availability. So actually this is the definition of potential. It is nothing but the amount of energy, or that is the amount of potential energy or work done. Work done is equal to energy. So amount of energy that is needed to do, to bring a unit quantity or infinitesimal quantity, and two things are very important. One is it will be in isothermal conditions, okay, and reversible. So the process should be isothermal and reversible while we talk about water, okay, or water potential. And free water, you know that it always has a potential of 0. and whenever the water is in some form of tension, it will have a potential negative. So, you will find that nowhere the water potential is positive. Free water is maximum, which is 0, free from any kind of salts and all that, but the for the soil water, because it is always in some form of tension, it will be negative. Okay. So, this concept of water potential was first given by Buckingham. And why do we take the potential energy? Because water in the soil is at a constant tension. So, we are not concerned with the kinetic energy because it is not flowing. Okay. And this water potential, it is composed of 4 different terms: gravitational potential, pressure potential, osmotic potential and metric potential. And we can express the soil water potential in these different units. So, you can take a look and you can work out the dimensions and SI units. I believe you can do that, but the common names, they are very important, you must remember that. And always remember that whenever we express the water potential, we express it in head units. Head unit is meter or centimeter, that is just the height. Okay. Just a second. Yeah, okay. So, now after reading about the soil moisture potentials, okay, just let me give you a brief explanation. So, I told you that there are 4 components of soil water potential: metric, gravitational, pressure potential and osmotic potential. So, this osmotic potential is actually due to the presence of salts in water, and metric potential, it is due to the tension by the solids. Gravitational potential is due to gravity and pressure potential is due to pressure. Okay, this is pressure. So, these 2 potentials are generally positive, and metric potential and osmotic potential, these are generally negative. Now, within that, wherever we are concerned with the soil water potential, our major concern is only the metric potential, because we will find very less amount of salts in our soil. So, we are excluding the osmotic potential, and at a particular level, suppose this is the level and you want to measure the water potential at all these points. So, the effect due to the gravity, it will be same. And for the pressure potential, it is due to the pressure of either above lying water table or air. So, whenever it is water table, it is called pneumatic potential. Okay, pneumatic potential. And always remember that your soil water is at a sub-atmospheric pressure. That means the pressure in your soil water, it is less than that of atmosphere. It is always at a sub-atmospheric pressure, your water. Now, this pressure potential term, we can also call that it is positive pressure potential, and sometimes the metric potential, we identify it as a component of the pressure potential and we call the metric potential as negative pressure potential. So, all you have to remember from this chart is what might be the positive or negative values of water and what are the implications, that is what is the meaning of each and every term in that. Now, we are moving on to a very important topic, which is hysteresis. So, hysteresis is nothing but it is the history of the soil moisture characteristic curve. So, before that, let me explain the soil moisture characteristic curve. So, it is a relationship. It is the relationship in between the metric suction and the volumetric water content. So, whenever I was explaining, I told you that metric suction is the major component of water potential that we take, and the soil moisture characteristic curve will depict that potential only. So, you see that on the y axis we have volumetric water content and on the x axis we have water potential. You can also invert the graph, okay. You can take the values to be in any axis, but your diagram must be right or your diagram should change accordingly. So, you see for the sandy soil, initially what is happening, the water content of sand is low, so it is starting from a lesser height, but for clay it is very high, so it is starting from a greater height. And in sand, you see that there is a sharp decline. Now, why is there a sharp decline? Because in sand, the infiltration or the permeability is very high than that of clay. Okay, a large number of macropores are present in soil. So, initially it will decrease rapidly, but then it will decrease gradually. But in case of clay, because the micropores they are greater than the macropores, the decrease will be very gradual. So, this is the relationship in between the texture and the volumetric water content. You can also read the graph for aggregated and compacted soils. Aggregated and compacted soils also you can take a look. But this is very important because it will tell you that what kind of a curve is this, okay, or why this happening, why that is happening, okay. Now, coming to hysteresis. So, this is just an implication of the soil moisture characteristic curve, okay. The SMCC was given by Childs. He was a scientist who gave the SMCC. And hysteresis is nothing but it is a phenomenon in which it is the history of the soil moisture characteristic curve. That means that this hysteresis will tell you that why there is a difference in between the absorption and desorption. So, hysteresis will state that at the same metric potential, if the metric potential is same, then there will be more water in desorption than during the wetting curve. So, this is what hysteresis states, okay. And these are the causes. Ink bottle effect means suppose the pores, the porosity, it is not continuous in your soil. So, here suppose the porosity is high, but whenever you are draining that water out, there might be the formation of several air spaces that might dominate. So, it will form the ink bottle effect. So, it is due to non-uniformity. Then contact angle variation. So, in case of contact angle, while we were studying, the advancing contact angle is always greater than the receding contact angle, but in case of drying, we are using the receding one, right. So, the contact angle will be less. Then there might be some air entrapped and that can act as an insulator, and if your soil swells or shrinks, then also it might result in the variation or in greater water content during the desorption cycle than during the sorption cycle. Okay. So, these are a few terms or a few important points regarding the soil water that you need to know. First, it is stating that what I stated, that the soil water potential is actually 0 for saturated soil, and there is a thing called air entry point. So, what is air entry point? When you are draining your soil initially, first the macropores will drain, but that macropore water needs to be replaced by air. So, the point or the tension at which air will start entering, that critical point, okay, where the air will start entering into your soil, it is called air entry point. So, first your water will drain and then at a particular point the air will come and replace the water, that is called air entry point. And larger pores empty at low suction and smaller pores they will empty at high suction. Obviously, if the pore is small, then there will be difficulty in suction. Water retention is much lower, that is 1 to 15 bars is much lower than that at -1 bar. Why? Because when you increase the tension, the availability of the water will also decrease. And another thing is that, okay, at high suction, the retention will depend on hydration thickness. So, what is this hydration thickness? Hydration thickness is, okay, just a second. So, yeah, the hydration thickness is whenever you are having a soil particle and a thin shell of hydration. So, suppose this is where water availability is very high, okay, but it might come or a stage might come when your water availability is very poor. So, in that case the water will be found as a very thin film, and this is generally related to hygroscopic water. So, this particular point or volume that is enveloping the entire soil structure is called hydration point, okay. And so, the soil moisture retention will depend on soil structure at low suction and soil texture at high suction. Very important point. Whenever your suction is low, okay, suction is low means the water availability is very high. Structure will govern that what is the SMCC. But if your soil water potential it is low, that means suction is very high. So, in that case it will be governed by texture, okay. Now, these are all the instruments that you should remember or learn, okay, while measuring the soil wetness. So, this is used to measure the soil wetness, I am saying, okay. So, we will just go one by one. Thermogravimetric method, it is the direct moisture estimation method, and all the others are indirect. Direct means you are directly calculating what is the percentage of moisture, but it is destructive. You will go in the field, you will take the soil sample, you will subtract the oven dry weight from the moist weight, and then you will find out the percentage of water that is present. So, it is mass of water, mass of moist soil minus oven dry soil by oven dry soil into 100, okay, into 100. So, this is the formula. Now, all of the other methods, they are all indirect methods. Indirect means you are not directly calculating what is the percentage of water, but you will calculate it through some other terms. For example, see the neutron moisture meter. So, in case of neutron moisture meter, what will happen? You will estimate that what are the number of slow neutrons, slow or thermalized neutrons are there after collision with the H nuclei. So, more number of H nuclei will suggest that more water is present. Similarly, in case of electrical conductance, you will measure the electrical conductivity. In case of time domain reflectometer, you will measure that what is the time, okay, with which the signal is returning back to you. If it takes longer time, that means more water availability. In case of gamma ray scanner, also this is similar to the neutron moisture meter, but a different kind of radioactive probe is used. Thermal conductivity by judging the soil temperature, and also advanced methods like that of remote sensing. So, for each and every method you have to know that who gave that particular method. So, I will just write some things down on the board, that who gave the particular method, what is the principle of each and every method, okay, what are the parts or components, and what is the relationship in between the moisture percentage and that particular moisture percentage and the components. So, these things you should know about each and every instrument present over there. Okay, what are their limitations and what are their advantages also, limitations and advantages, okay. So, these all things you can find it in any standard book, okay. You should go through it and memorize it because it is very important for your JRF. Now, in that slide we measured that what is the percentage of soil moisture wetness, but in this slide we will measure that soil moisture suction, okay, or potential, that is matrix suction or matrix potential we are going to measure, and a very good instrument to do that is tensiometer. So, tensiometer will measure the matrix potential of your soil, and from the figure you can see that there are actually two kinds of tensiometer. Initially it had a manometer scale, that is a pressure measuring device, this manometer, and now it has been replaced with the help of a vacuum gauge. So, whenever you insert, and this is a porous cup that is present in each and every tensiometer. So, whenever you insert the tensiometer in your soil, depending on the soil matrix suction, either the water will come out or the water will come inside the tensiometer, and there will be the changes in pressure that will be reflected in these two instruments, and from the change in pressure through the help of this formula you can estimate that what is the moisture concentration, what is the matrix suction, okay. And always remember that a tensiometer can only measure it up to minus 0.85 bars. So, this value it lies for nearly dry soil, nearly dry and sandy soil only, the tensiometer can measure the moisture, and it can never measure the osmotic potential because the holes of the porous cup, they are large enough, okay. So, it can never measure osmotic potential, it cannot, okay. Okay, so now we will come to the flow of water. So, we had measured that what are the concepts of just a second. So we had measured that. What are the concepts by which you can measure the soil water? Cannot be used in, no, it cannot be used in clay soil. It will only be used in sandy soil, and that too at a very dry range of soil. So flow of water is actually governed by several equations. So we will go one by one. First is Bernoulli's equation. So this is just the mathematical expression of Bernoulli's equation, and it will state that the energy state of water. So this is a sum total of energy state of water, and what kind of energy states we are considering? We are considering the velocity gradient, then the mass density and the pressure. So we are considering the velocity density, mass density and the pressure at a height above the reference level. So suppose this is Z, this is your reference level, and you are considering the flow of a fluid at this particular height. So this Z will give you the reference level, and it is for an incompressible non-viscous fluid. So here we are not measuring the viscosity, we are assuming that the fluid is ideal, and the sum of its kinetic energy, pressure energy and potential energy per unit volume is constant along the streamline. So here we are also considering the streamline flow, not the turbulent one. Clear? So this is the sum of all these three energy heads that you have to remember, and what kind of a fluid it is valid for. The next one is Poiseuille's law. So this will deal with a viscous fluid. This will deal with a viscous fluid, and it will state that it is directly proportional to the fourth power of its radius. So this comes. Please remember this equation. Okay, and the Poiseuille's law, it is valid for a viscous fluid flowing through a tube. Clear? So in both the cases, they will assume that the flow is steady. Now what is steady state flow? I will tell you later on. Okay, and the pressure is also constant along a particular cross sectional area. Then another thing came, which is called Reynolds number. So Reynolds number will actually help you determine that whether or not your flow is laminar or turbulent. Laminar flow means what? Laminar flow means when all the layers, they move in a same direction with the same velocity. But turbulent flow is whenever one layer is moving, okay, so they will be moving at different rates and different densities, so they will not be parallel, okay, to one another, and Reynolds number will help you tell that. So this line is very important, ratio of inertial force to the frictional force, and these are the different critical limits for Reynolds number. Always remember that it is different for soil as well as for pipe, okay. So here comes the steady state flow. So steady state flow means that it is the flux, okay, the flux, that is dq per unit gradient of water will be equal to the change in volumetric moisture content per unit time, okay. So that means the hydraulic gradient of a particular system will remain constant. So the flux will remain constant and equal, and this is mainly limited to saturated flow. The hydraulic gradient at each and every point will be equal, and the dq by dx, that is the unit change in flux with distance, is equal to the unit change in volumetric moisture content with time. But for the transient flow, so here in case of steady state, inflow is equal to outflow. But for this transient flow, this will not remain constant. So this is the basic difference. And Darcy's law of water flow that we will just deal with, it was given in sandy soil in saturated condition for steady state flow only. But for transient flow, this law is not valid. That is why two scientists, one is Buckingham and the other is Richards, they actually modified Darcy's equation. I will tell you that. So just before that, let us come to the concept of hydraulic. Okay. So first let me tell you that only. So Darcy's law, that is also very similar to that of what we had read. So it is, this is the flux, that is Q by AT. It will be directly proportional to the hydraulic gradient, that is del H by L. Okay. So he said, or Darcy mentioned that, okay, so first let us read that what is the concept of hydraulic head. Hydraulic head, it is a potential potential energy per unit weight. So when I was telling you the different units of potential, I told you that we always measure the water potential in head unit, right? That is meter or centimeter, and hydraulic head is potential energy per unit weight. And the differences in hydraulic head from one point to the other will govern the potential. So, there needs to be some difference, right, for the flow of water. So, a place where the hydraulic head is higher, from there water will flow to a place where the hydraulic head is lower, and the hydraulic head, it is actually the sum total of gravity head as well as pressure head. So, this is for a saturated soil and this is for an unsaturated soil. This is a figure which is just for your reference. Okay. Now, for a saturated soil, it is measured by a piezometer, and for the unsaturated soil, it is measured by a tensiometer. So, this is the concept of hydraulic head. And Darcy actually stated that it is for steady state flow. But later on, this guy called Buckingham, he came and he said that no. Buckingham said that no, it does not depend on that. But whenever I am writing this K into del H by L, K is its hydraulic conductivity, he said that this hydraulic conductivity of our soil water, it will depend on the volumetric water content. Volumetric water content. And then there was another guy whose name was Richards, and he said that okay, no, this K will depend on the metric potential. K will depend on the metric potential. So, these are the two different theories that were developed after Darcy's law was given in saturated soil. So, Buckingham said that it will depend on the volumetric water content, and Richards said that it will depend on metric potential. But there is a catch. Whenever you are considering volumetric water content, that means you are considering the entire geometry of your soil. So, for theta, you will consider entire soil geometry. And that is obviously a better indicator than the metric potential of your soil. So, volumetric water content is a better indicator than the metric potential of your soil for hydraulic conductivity. Clear? So, this was all about the flow, okay, and hydraulic conductivity has the same unit. You can easily find it out with Q as the volume and A as the area and L is the time. So, for all these units also you have to be very clear with what are the units of hydraulic conductivity, pressure head, gravity head, chemical potential, all that. Now, we will just start with another process of entry of water into the soil, which is called infiltration. So, when the water is moving from the soil air to the water, it is called infiltration, and it is governed with two things. One is infiltration rate. Rate means how much water is moving inside the soil. So, it is centimeter per hour, and cumulative infiltration means it is only centimeter or millimeter, that is how much it has moved. So, you can see that with time the infiltration rate will decrease because the soil will reach a basic capacity. So, the soil will reach a capacity, okay, where it cannot take in more water. So, this particular constant rate is called basic infiltration rate, where it cannot take in more water. So, it will decrease with time. But for the cumulative infiltration rate, obviously your infiltration is happening in your soil. So, the cumulative infiltration rate will increase with time. So, these are the two things that you should remember. So, these are the zones of infiltration, again very important. First is saturated zone. So, in case of saturated zone, when the water is entering, obviously it will be filled. So, all the pore spaces are filled. Then transition zone. So, it is just a transition from saturated to unsaturated soil. So, the water content will rapidly decrease with depth. Then in the transmission zone, what will happen? The water content or the hydraulic gradient in this zone, it will be uniform. So, it is a lengthening unsaturated zone with uniform higher water content. So, the water content will be uniform. So, you can see from here that this hasn't changed. So, this is the water content, okay, this hasn't changed, and this is the transmission zone. Then, we can have the wetting zone and the wetting front, okay. So, wetting zone means here up to this level only the soil can get saturated, and beyond this there is a complete zone of unsaturation, and that is called wetting front. So, there will be a sharp decline in the water content along with this zone. So, with that we come to the end of the lecture, and this is the last topic, which is soil plant atmospheric continuum. So, in the soil plant atmospheric continuum, it just states that how the water is recycled in between soil, plant, atmosphere. Okay. So, this concept was given by Phillips, and these are all the features, that the water is a continuous hydraulic system, gradients are there, and it is always in the form of liquid or vapor, never solid, and a number of resistances are there. So, because of these resistances, the flow will be varied, and it is analogous to an electrical system, because in electricity what happens? It will always move from a zone of lower resistance to that of a higher resistance. So, you see that you have to remember these values, the different potentials for the soil, plant and water, and out of that you will find that the maximum is for leaf. That means every water, whether it is present in soil or atmosphere, ultimately it will reach the leaf. Okay. So, this was the end of our soil physics marathon. If you want to cover all the things of soil, water along with detailed explanations and mathematical questions in details, you can always subscribe to our master course where I had already explained these concepts in details, taking multiple classes, okay, because it needs understanding. Even though if you like our marathon, you can always subscribe to our master course, or you can also go and attend the mock tests. And if you liked today's session, then please be with us, because we will be continuing the different marathons of chemistry, fertility in the upcoming days, and we want your full participation and full attention in that series. And thank you guys for being with me for so long. Thank you.